So thank you everybody for joining, and probably most of you know Oliver by now. Oliver's at Imperial and has in the past done lots of work on sequences from Rakai with the whole team, with Kate and Tom and Joseph, and we're looking forward to sort of hearing the latest update on the research at Imperial.
Great, thank you, Lucy. Fantastic. So hello everyone. Thank you for dialing in. I'm pretty sure you're busy with many things. And so I hope I keep you entertained for the next 45 minutes or so. I wanted to talk today about our more recent work on estimating age-specific transmission dynamics. That is primarily based on deep sequence analysis from data in Rakai, Uganda, but also from the UVI, like a little bit further up north in southeastern Uganda. And the people who primarily drove the work, so that's Joe, but Nicolas Bosa has also done contributions, and I'm pretty much just summarizing and trying to put things into context. I'll also mute my video, just hopefully that'll help with the quality as well. But let me know if anything is unclear, and I'll try and rephrase or just say it one more time. So the thanks, Lucy, for the next slide. So the idea that really got us going and with these analysis was the paper by Tullio in 2017, which, as you know, got a lot of coverage. But the idea of this HIV transmission cycle that young women, adolescent and young women between 16 and 25 are primarily infected by much older men, between 23, maybe 25 to 35, and then age in a way, and as they become older, then reinfect men of similar age. So that was kind of this idea was put forward as the predominant cycle of HIV transmission, how it regenerates to new generations, and we got really excited by these ideas. And if you, Lucy, if you could do the next slide. And I wanted to talk a little bit about this study. So this was a phylogenetic analysis based on Sanger sequencing data, and there were 90 heterosexual transmission clusters, which they showed in their figure number 2. So they made this plot, and you can see these clusters. I believe the women must be in red, and the man in gray, and the ages are given in numbers in there. So they analyzed essentially these cluster pairings. So they didn't, from the phylogenetics, they didn't have evidence into the direction of transmission, but they just looked at these linkages. Lucy, if you could do the next slide, please. And so when they looked at all possible male-female pairings, they made the table that I just show you now on the left-hand side. So where they looked at pairings from involving women that were less than 25 years old, 25 to 40, or above 42 to 49, and then with the corresponding age categories in the men. And so really the astounding figure, or one of the astounding summary statistics from this analysis was that when we look at women who were aged less than 25 and look at with what men they were linking it in the phylogenetics, so we saw that there were 60 pairings involving women less than 25 years old, and 42 of them were linking with men who were older than 25 years. So that was 70%, and that's quite an astonishingly high figure. And when they looked at the age difference involving women of age less than 25, they found with any man, so that's how I understood the paper, the average age difference was 8.7 years. So these were the phylogenetic linkages. And that suggests that these age discordant pairings, these particular pairings of young women and much older men, may be an important driver of the epidemic. And so that got us really hooked on these results. Lucy, if you could do the next slide, please. And that was in particular because we had just a little bit before read the paper by from the Voice trial that was reporting on HIV incidence and the association with partner age. That was from the South African trial sites, and that was data primarily from the Durban area in 2009 to 2012, so just a bit earlier, but not much, but more in the Durban area, not in the rural bits of KwaZulu-Natal. So they had 3,789 women enrolled, and 2,149 of them were aged less than 25. And they looked at what so the women reported on their primary partner, and then the age of that partner. And then they in the study they compared HIV incidence stratified by age of the predominant partner. And what they found in univariate models, but also multivariable models adjusting for other non-risk factors, that there was no association with age discordancy, so having a primary partner older than 5 years, and HIV incidence. So in that study suggested that age discordant relationships may not be a driver of the epidemic amongst young women. And so in this context, we found the phylogenetic results very interesting and wanted to look at them further. Lucy, if you could do the next slide, please. And then after that, so we also looked at Adam's paper, who's on the call, who looked at HIV incidence estimates, and also the association with partner age, and that was an observational study from the Africa Center Demographic Surveillance Site, 2004 to 2015. So there were 10,260 women, and 7,251 of them reported the age of the most recent partner. And what we found really striking was how these HIV incidence estimates really varied depending on reporting behavior. So on the left-hand side, you see HIV incidence amongst all these women who then during follow-up were HIV positive. And in pink it's the women, and in blue it's the men. And you see like these exorbitantly high incidence rates peaking at 7 per 100 person years, so absolutely crazy. And then on the right-hand side, you see the same estimates amongst women, only considering women who reported the age of the most recent partner. And Adam, if I talk any nonsense, please interrupt. But so it was just, I think, like just getting this feeling that what individuals report may have a substantial impact on what is estimated. And if you could, Lucy, if you could do the next slide. And with that in mind, when we look at the results in Adam's paper, where they essentially did estimated HIV incidence by age of the female respondent, shown on the y-axis, and the primary male partner on the x-axis. You see, especially amongst the very young women, like age 15 to 20, how HIV incidence rates are much higher when these women reported a much older partner, as long as that partner was not older than 35. So in a way, that study then supported Tullio's phylogenetic analysis, but there was always this this kind of lingering thought, and I'm very grateful for Adam to have put his first figure into the paper, how these incidence estimates may depend on reporting behavior. So that got us started with the phylogenetic analysis. Lucy, if you could do the next slide, please. And the study objective was specifically to look at these young women and estimate the proportion of infections amongst young women that are attributable to older men using deep sequence data from PANGEA. And we focused on southeastern Uganda, including data from the MRC UVRI and Rakai. And that the idea was to complement essentially Tullio's study, but also using deep sequence data. Lucy, if I could have the next slide, please. Okay, in terms of the study setting, the data at the UVRI were collected between 2014 to 2017, involved 10 fishing sites and 6 locations where there was a general population further inland. So there were 3 such there were 6 such locations, and then there were also women at high risk of HIV infection, but they were not included in the analysis that I'm just about to present. And this is a figure from Nicholas's just very recent paper that appeared in Viruses. Lucy, if I could have the next slide. So there were approximately 2,500 individuals who attended HIV clinics or participated in intervention campaigns, and so of those 2,500 could be deep sequenced, and this is the data that we analyzed. And amongst those, we found in total 72 source recipient pairs, essentially using the protocol, the phyloscanner protocol. And of those, 22 pairs involved a female recipient that was less of 25 years old at time of enrollment. And we were able to adjust for heterogeneity in sequence sampling by gender and location. And so these are the estimates that we obtained. So we estimated that, considering the women aged 18 to 24, we estimated that 65% acquired HIV from men who were 25 and 59. Of course, the confidence intervals were quite large considering the small sample size, but it was pretty much in line with what Tullio had estimated for KwaZulu-Natal in South Africa. Lucy, if I could have the next slide, please. And so with these kind of first estimates, we then considered the data from Rakai. That was the samples were collected between 2011 and 2015, and the data is essentially the same as that was reported in the Lancet HIV paper that came out earlier this year as well. Lucy, if I could have the next slide. So the main difference here was that this was a cross-sectional survey that was preceded by a household census. So we had a very good idea of the actual population that was eligible to participate, that then participated, and that then was sequenced. And so we were hoping that this additional analysis would give us a much better handle on potential sampling biases and how they affect our inferences. So in total, we had sequence data from also roughly 2,500 individuals, and we found 293 source recipient pairs in this analysis. Lucy, if I could have the next slide. And so this is probably a figure that you haven't seen before. So these are the 293 pairs, but plotted by age of the transmitter and recipient. So the age of the transmitter is shown on the x-axis, and the age of the recipient is shown on the y-axis. And the age is taken at time of at the midpoint of the study period. So how old were these individuals at the midpoint of the study period? And we had in total 120 source recipient pairs where we thought that phylogenetics strongly indicated transmission from women to men, and 173 from men to women. And in total, there were 96 source recipient pairs that involved women less than 25 years, and there were 57 source recipient pairs with a female recipient less than 25 years. So we had so we could directly estimate the sources of infection for 57 women that were older than that were younger than 25 years. And that is not a very large sample size. So we tried to borrow strength through a Bayesian analysis that essentially does, it's a Gaussian process-based analysis, but essentially does the same like kernel density estimation. So it's smoothing over different age categories. And I'll try and give you a visual impression of that in just the next few slides. Lucy, if I could have the next one, please. And the particular feature of this analysis is that it just doesn't only do like some sort of kernel density estimation through these points, but it attempts to adjust for possible sampling biases. And we know that they are present in the data. So I'm showing you here the probability of participation. So what's the probability that men and women of different ages participated in the RCCS cross-sectional survey? And I'm showing this to you by fishing sites and inland communities. And generally, participation rates were lower amongst younger individuals simply because they were at school or just away for work. So that was the primary reason why individuals didn't participate. Lucy, if I could have the next one. So what I'm showing you here is then the fit of the overall statistical flow model after accounting for sampling heterogeneity. And then on the left, I'm still including in red points the actual data points for female to male transmission, and then the fitted model on top of it without contours. So the fitted model is shown in colors, and the contours correspond to some standard kernel density as fit to the red points, to the raw data. And then on the right-hand side, you see the same for transmissions from male to female. And the transmitters are shown on the x-axis and the recipients on the y-axis. So I would say the fit is fairly reasonable. There are probably like a few points you can see, like if you look at male to female transmission, there are like a few bulges in terms of the red points, and they're not really captured with they smoothed away with our statistical model. Sort of reflecting the sample size. So the model prefers to be have a more regularized estimate of transmission flows, considering the number of data points that form kind of like some weird patterns. Considering, like, for example, male transmitters around just below age 40 with female recipients that are around age 45. So these are not represented in our statistical fits and anything what comes after this slide. If I could have the next one, Lucy. So I thought it's probably easiest to start with some fairly simple summaries. So we looked at the ages of sources. So on the left-hand side, you see we're looking at male to female transmission. So what's the probability that a woman is infected by a man aged 25, 30, 35, 40, and so forth? And so one distinctive feature of our Gaussian process-based model is that we are not bound to looking at particular age categories. So we can really go down to 1-year age bands and get non-parametric estimates like across 1-year age bands of the by male sources. So you can see that most of the infections that we observed in women are attributed to, so it's peaking at men who are of age 29, but it's quite broad. So 50% of infections in women are attributed to men aged 26 and 37. So it's not a particular risk group that is transmitting to all women. It's quite broad. If we look at transmission to men on the right-hand side, we see it's peaking earlier. So it's peaking at age 25, and 50% of infections in men are attributed to women aged 23 to 34. So it's a slightly more narrow, but still a very broad age range of women who are transmitting onward and are, based on our data, the primary sources of infection in men. Lucy, if I could have the next slide, please. Now, where it starts to be interesting is when we stratify by age of recipient. So what I'm showing you now is essentially the same analysis. I'm looking at the probability that women are infected by men of different ages, and the ages of the men are shown on the x-axis in the left plot. So it's the analog of the figures in the previous slide. The only difference I'm doing is like I'm conditioning on the age of the recipient. So for example, if I'm looking at the darkest blue curve, so I'm considering female recipients of age 15 to 16, and we are estimating who are their male sources and what age did they have. And you can see that these male sources, like they peak at around age 26, and you can see that there is a bit of a sort of an interesting long tail. So it goes up to age 42 until it sort of like dips at the very end. So quite a characteristic curve that is certainly not Gaussian or anything like that. So that speaks to this ability to do non-parametric inference with these Gaussian-based process models. And then if we look at, for example, the yellow curve, so that corresponds to women aged 49 to 50. And we are estimating what are the ages of men that are these women are infected by. And what we see is that from the data, what we estimate is that these men are younger, so it peaks at probably age 38. It certainly has a range, but this tends to be younger men, not of the same age. And we can do the same for transmission from men to women. On the right-hand side, we are looking at the ages of the female sources for two men of different ages. So I think you can probably see that if you're looking at very young men, for instance, we don't have this very long tail on the right-hand side. So there don't seem to be these very old men who are contributing to infection in very young women. Are there any? This is probably a very difficult slide to digest. If there are any questions at this point, I'm very happy to take them. No. I should say, of course, so these are the curves that you're seeing. These are posterior mean estimates. There's, of course, substantial uncertainty in these numbers. I need to apologize. I wanted to include that slide. I didn't. But I want to make you aware that there is uncertainty in these numbers, and we can report that, and we should report it. And the uncertainty is largest at the ends of the spectrum. So when we're looking at very young recipients and very old recipients, regardless of gender. Lucy, if I could have the next slide, please. And so this is sort of like a slightly different view of the same figure, but with the confidence intervals included. And I'm focusing here on the age difference between sources and recipients in male to female transmission and female to male transmission. So on the left-hand side, we're looking at female recipients. So this is male to female transmission. And so we're asking, so what's the typical age of the male sources? And what we found is that, well, if you're looking at very young women, like aged 15 to 25, their male sources tend to be older, often much older. So sort of between 29 and 30 years on average. But then you can see it flips around. So then if we're looking at transmission to older women, so say women of age 40 or 45, they tend to be predominantly infected by younger men. So it's sort of challenging this this idea of looking at just the constant age differences as a whole, because these dynamics, they seem to flip around at some point. And it sort of like speaks a little bit to the analysis that Adam was doing on the Africa Center data, where it just wasn't necessarily always older men who then transmitted to women of any age, but it was this kind of middle group of 25 to 35-year-old men who really seemed to be the main sources. And in our case, we estimated that half of the infections are from men aged 26 to 37, so very similar. And I'm contrasting this to the situation in male recipients on the right-hand side. So we see that very young men tend to be infected also by older men, but nearly not as strongly as for male to female transmission. And we also see that it flips around much more rapidly. So men aged above 25, they tend to be infected by younger women in our data. Thank you, Lucy. If I could have the next one, please. And so we then kind of tried to link up a bit more with the existing literature and looked specifically at age discordant relationships as they are typically defined, either having a partner that is 5 years older or 10 years older. And what I'm showing you here is I'm looking at male to female transmission, and I'm asking, what is the probability that transmission occurred from a man that is 5 years older, at least 5 years older in red, or at least 10 years older in blue? And you can see how this varies. Sorry, the label on the x-axis is incorrect, so it should read age of female recipient. So I repeat that. So the x-axis should be age of female recipient. So we are asking, for example, looking at women aged 20, what's the probability that they are infected by a man at least 5 years older? And what we find is it's about 80%. And there's, of course, a 95% credibility interval, and that goes from roughly 70% to 87%, just looking at the figure. And we can do the same, asking what's the probability that a female recipient aged 20 is infected by a male source aged 10 years, at least 10 years or older, and we find that this is, we estimate that this is 45%, with a 95% credibility interval of, I believe, 32 to 57%. So very high contribution from much older men to young women in particular. Thank you, Lucy. Could I have the next one, please? So I'm already coming to summarize the main findings so far. So considering the data from Rakai, this very unusually dense sequence sampling in a cross-sectional setting where we understand the population denominators. So there were roughly 2,600 deep sequence samples. We found 293 pairs. If we look at these, we estimate that overall half of all infections in women were attributed to men aged 26 to 37, and approximately half of all infections in men were attributed to women aged 23 to 34. However, the mean age of the source case depended on the age of the recipient and, of course, on gender. And so what we found was that women aged above 35 were typically infected by younger men, and men aged above 25 were typically infected by younger women. We looked into the sources of young women in particular, and we found that most young women aged 15 to 24 were infected by men who are at least 5 years older. And the estimates range from 91% for women aged 15 to, so 90% of these women are estimated to have acquired HIV from a man at least 5 years older. And this declined to 73% at age 20 of the women and 51% at age 25 of them. Thank you, Lucy. I have one more slide. And I'm very keen to have any questions you may have and comments or suggestions. Looking at this problem much more broadly, or looking at HIV incidence estimations and associations with age discordancy and so forth. Just because I think it's a very important problem, considering the youth bulge, like considering how many, just the age pyramid of the individuals, which I'm showing here for Rakai on the left-hand side. So there's just so many young people. And then if you compare this to the very steep rises in HIV prevalence, both in the fishing communities and inland communities, especially amongst women, I think I'd be very keen to kind of discuss these results more broadly in the PANGEA group further. And with that, I'd just like to very quickly acknowledge everyone involved. Lucy, if you just have the last slide, please. So of course, like the entire Rakai team, but also at the MRC, UBI, and LSHTM Uganda Research Unit, especially Nicolas. Zhou Yu has done, so my PhD student, Zhou Yu, she has done essentially all the implementation and most of the modeling that is underlying these results. And of course, all the study participants as well, and Lucy for running the PANGEA meetings and management so well these days. Thank you very much.